Hey everyone, it's Mr. Ference. Hope you're doing all right. We are going to pick back up with part 2 of our lecture on fluid dynamics. This whole video is going to be about one equation. It is a big one. It is an important one. So let's get down to it. In the 1700s, this guy Bernoulli figured out that when the velocity of a fluid increases, that its pressure will actually decrease. There's this inverse relationship, and this happens as a result of the conservation of energy. But keep in mind that we've been talking about how pressure will change with the height or the depth of a fluid. So if we have a pipe, for example, that is changing the height or the depth where water, or whatever fluid is flowing through it, the pressure is also going to change. And of course, we talked about last video, if the size of the pipe is actually changing as well, that'll change the velocity. So all of these are very closely related to each other. And that's what we're going to look at with this equation. So Bernoulli figured out that there's this relationship between these three quantities, with pressure, with velocity, and with height or depth. And that's what he has in these three terms of the equation. This first term is the pressure. This second term talks about the density, but also the velocity of the fluid. And then this third term here is talking about the density, but mainly the height and the depth. And what he found was that the sum of these three things is constant. Just like we were talking about in the last video. If this sum is constant, if we compare these three quantities at one point or another, we're going to find that the sum at point 1 is going to be equal to the sum of these things at point 2. And so that's where we get this Bernoulli equation. Let's take a look at it. It is big. It looks complicated, but when we look at it more closely, we'll see it's fairly simple. This is Bernoulli's equation. Write this one down. This is one of the major ones in the unit. This is actually one of my favorite equations in all of science, and we'll talk about why that is. Keep in mind that the three things we're really looking at with this are velocity and pressure and the depth or the height. So if you look at this equation, what we'll see is that each side matches the other. The only things that are changing from the left side to the right are the subscripts. The first term on each side of this equation has to do with the pressure. So we're looking at the pressure at point 1 and the pressure at point 2. The second term here, we're looking at the velocity at point 1, the velocity at point 2. And that may change depending on the size of the pipe, right? We can use that continuity equation to figure it out. Keep in mind here that this term also kind of looks like the equation for kinetic energy. This comes from the conservation of energy, so that would make sense that we're seeing that. And then this third term here is talking about the height or the depth of the fluid. And again, this sort of looks like gravitational potential energy, right? So these are, like I said, the left side here and the right side here match. We're just changing the subscripts and looking at those three things at point 1 and those three things at point 2. Keep in mind also that the density of the fluid will usually stay constant. So the other thing to keep in mind with this is like it said, it looks big and messy, but this equation is what we call generic and universal. What that means is it is, as written, going to work everywhere in the universe. And as we're looking at specific situations, many of these terms will become zero, they'll cancel out. We'll look at what something like that looks like, and also as we work through some example problems. But the reason this is one of my favorite equations in all of science is because it has so many applications. This is the reason that airplanes can fly. The main relationship to take away from this equation is that there is that inverse relationship between volume and pressure. Velocity. Between velocity and pressure. As velocity goes up, pressure goes down. So that's what we see here with this airplane wing. The shape of an airplane wing and the angle at which it meets the incoming air is such that the air being deflected over the top is going to go faster than the air on the bottom. Because of Bernoulli's principle, that means that the pressure on the top of the wing will be less, and that will create almost a buoyant force pushing the wing up. We see the same thing with a sailing boat. Okay, so this is a top-down view of a sail on the mast of a boat. This is why sailing boats can sail. The angle at which this sail meets the wind is such that, right, the air going in front is going to be moving faster than the air in back. It creates that pressure differential, and the boat gets pulled or pushed in the direction of that pressure differential towards that lower pressure. This is also why curveballs can be a thing. It's called the Magnus Effect. So if you've seen the video of that dude dropping the basketball, what happens as a ball is traveling through the air, as it's rotating or spinning, that means that the air on either side of the ball will be moving differently at different speeds. And so different speeds means we have different air pressures. And so it'll actually get pulled to the side. This is also why chimneys work. The wind blowing over the top of a chimney, higher velocity means we have that lower pressure area, which will suck the smoke up out of the chimney rather than just letting it fill the room that you're sitting in and enjoying that fire. There's another specific application of this called where we'll talk about what it's called, where we're looking at a water tank, right? Some container full of a fluid, and there's like a spigot or a tap on the side of it. Once we open that spigot up, the water or whatever fluid is going to come out of the spigot at some given velocity. And we can use Bernoulli's equation to actually calculate what that velocity is going to be. So a couple of things before we get into it. The first thing I want to clarify is that the top of this container is open. Okay, so it's open to normal air pressure. Excuse me. It's open to normal air pressure. So here's the sort of unedited version of Bernoulli's equation here. We're going to cancel some things out. So the first thing I want to cancel out is this V2. So keep in mind here, the water sitting here at the top is basically at rest. Maybe not entirely mathematically, but we can sort of round it off to be zero. What that means is this whole term is just going to disappear. The other thing is that because this is open to atmospheric pressure, the pressure up here and the pressure down here, because this spigot is also open to atmospheric pressure, these are going to be the same. So the pressure terms will also cancel out. It's not that the pressure is zero, it's just that they're the same, so we can just subtract them from both sides. We can also cancel out the rho, this density, because we're using the same fluid, right? This is just water or whatever. The density is going to be the same. So we can see already this big, long, complicated looking equation is going to get very, very simple. We're left with just these two terms over here on the left and just this term here on the right. To make things a little bit easier for us to rearrange, I'm going to multiply everything by 2. That's going to give me v1 squared plus 2gy1 equals 2gy2. And of course, we can move this term here over to the other side. We'll take the square root. And what we'll end up getting is this. This equation is not on your AP equation sheet, but you can derive it from Bernoulli's equation just like I did. So just keep in mind pressure and density are going to cancel out. V2 will be 0, basically, because it's at rest. What this equation tells us, this equation is called Toricellis Theorem because this was figured out by some old dead Italian dude. What this equation tells us is that the speed that this water or whatever is going to come out of this spigot is only really dependent on the distance between the top of the liquid, wherever it is, and the height of the spigot. So if you have a tank or some container or something, and you open it up, as that drains and that height starts decreasing, what you're actually going to see is that the velocity of the fluid coming out of that tap will decrease. You can do this at home. You will find that this is true. The other kind of cool thing in terms of bringing back some stuff from AP Physics 1 is that as this fluid comes out of the spigot here, we can treat the water as a projectile being launched horizontally. So we can use our kinematics equations, our equations of projectile motion, and actually calculate where that water is going to land. I think I have an FRQ sitting around somewhere where we're going to do that. But anyway, this is Bernoulli's equation. Make sure that you feel comfortable looking at it and sort of picking out the different pieces of the equation. We will practice using it to solve a little bit later on, but that is going to wrap it up. So talk to you later. Take care of yourself. See you around.